Welcome back. This is the last day of the OPC Day International 2021. Good morning, good evening, depending on where you are in the region in the world here. I'm super excited, obviously, that today we focus a complete day on available solutions, but also on existing success stories from big companies around the world. So it's a pleasure for me at the beginning to have two vendors which I selected for specific reasons. Eugen Schibli from Mettler Toledo in Switzerland. He will introduce himself later on in more detail. I can't remember the year, I have to figure out that, multiple years ago, where I presented in Switzerland in front of a big audience. And I know when it was 2017, something like that, 16, 17. And I wanted to report about a multi-vendor demo, what we had done since the year 2015 yearly at the SAP booth on Hanover Trade Show. And the Mettler Toledo weighing system was involved into that demo, together with multiple other devices. And I was proudly reporting to the audience that I was staying next to the preparation group, and it took just 20 minutes to include that asset into SAP. And Eugen Schibli was in the audience, and he stand up and said, "Mr. Hoppe, I have to correct you. That's wrong. That's not correct." And obviously, in that momentum, remember the situation. You are a presenter in a big audience. I was starting. Oh, this could become an interesting direction. But he just corrected me. Hey, it was much quicker. It just took half of the time. That's a perfect correction, and we all know that people from Switzerland are very precisely as always. So this is why I selected Eugen Schibli. He is super engaged as a leader of the chair of the joint working group between the OPC Foundation and the weighing group of the VDMA. And second, I invited Dr. Horst Heinol-Heikkinen from Asentics, camera system. He also is super active. He was also in this 2015 demo, inspiring the world with integrating OPC UA into these intelligent systems, camera systems for configuration, but also with a clear vision to make this an international standard, being adapted and accepted in multiple regions in the world. And this is what I believe is just perfect. Starting something, but a standard is only a standard if it gets adapted in the world. The best paper just being somewhere and being just a perfect academic paper is not an accepted standard. And what we want is, obviously, we want OPC UA to be an accepted standard, and that's what happened over all the last years. So this was a little bit introduction on why I selected these two companies. I know that there are multiple other members and people having actively contributed in that groups. Unbelievable many people have come together, shared vision, and worked together on the vision to work on standardized data. Obviously, I can't name them all, and I can't, from the over 65 groups where we have 32 released companion specification, I can't bring in one example of all these groups. So please allow me to just select the two of them, which we hear now at the beginning. After we have these two presentations from two vendors, we have about 5 presentations from big end users. It's Equinor, it's BASF, it's Renault, it's BMW, and its company Miele. And Miele is about 10 kilometers from where here this TV studio here at my home is. Okay, with this introduction, please remember put questions into the Q&A. Mr. Schibli is online already. We have the colleagues from yesterday online also. Peter Lutz is online. Erich Bahnstedt for all the IT questions is online. I welcome everybody back, but let's run the first presenter, and I'm handing over to Eugen Schibli.
Hello and welcome to my presentation. My name is Eugen Schibli. I'm based at Mettler Toledo in Switzerland. Within Mettler Toledo, I'm marketing manager for the Industrial Internet of Things, or Industry 4.0. I'm responsible for weighing in production. In the next 10 minutes, I'm going to introduce you to how Mettler Toledo implemented OPC UA into weighing equipment for manufacturing. Thank you for attending my presentation. To start my presentation, please allow me to introduce Mettler Toledo. Mettler Toledo produces and services measuring instruments along the entire value chain, from incoming of goods to laboratory to production, quality control, logistics, and finally for retailers. Our products are used for manufacturing of pharmaceuticals, chemicals, food, automotive parts, plastics, raw materials, and for logistics for these industries. The company has 16,500 employees. We have a turnover of a little bit more than $3 billion. A remarkable fact of Mettler Toledo is that we have more than 8,000 direct sales and direct service specialists all over the world. With this large number, we are one of the largest global service organizations among precision instrument manufacturers. On this slide, I explain the current and also the future communication architecture in industrial production. On the slide, you see two different architectures. The triangle on the left is the well-known SCADA pyramid. It includes, from the bottom to the top, data exchange in industrial production, from sensors to actuators, to machine control, to process control, to the MES, to the ERP, and finally to the cloud. In the traditional SCADA automation pyramid, data is consistently forwarded in a systematic step-by-step process following the hierarchy. Communication is via networks such as Profinet and Ethernet IP, but realistically also serial point-to-point connections such as RS-232 or even 4 to 20 milliamperes. On the right-hand side, you see the illustration of any-to-any. Any-to-any stands for everyone communicates directly with everyone. With any-to-any applications, sensors and actuators communicate directly. The communication ignores the strict hierarchy levels of SCADA. I have to point out, today, time-critical data is not communicated via any-to-any, but this will change in the future. On this graphic, you can see the distribution of the communication technologies. On the vertical axle, you see Ethernet not deterministic, and at the bottom, industrial Ethernet deterministic. On the horizontal axle, you see small data volume time critical, and on the right, large data volume non-time critical. On the right-hand side vertical axle, on top is MES ERP cloud, in the middle machine-to-machine control, and at the bottom sensor to machine and sensor to sensor, sensor to actuator. The blue field here illustrates the territory of OPC UA and MQTT. The green surface here illustrates the territory of Profinet, Ethernet IP and other such technologies. In the middle, we have the mixed zone. In the mixed zones, both technology groups are being used. And who uses what depends on the industry, on the customers, and on the applications. Here is the same graphic again. So, what kind of evolution can we expect? We will receive Ethernet time-sensitive network. We will receive OPC UA pops up. We will receive OPC UA field-level communication. And it will become common that multiple communication technologies share one network wire. These new technologies will change the size and placement of the territories shown. The blue zone for OPC UA and MQTT will grow. The green zone for Profinet, Ethernet IP and other technologies will shrink. The mixed zone will grow and move down because new technologies change the landscape. The described scenario poses a challenge for an equipment manufacturer. We asked ourselves, when does the above scenario become reality? What do we offer to our customers today? How do we implement OPC UA for the whole product range? And how do we upgrade the installed base of our customers? On the previous 3 slides, I showed you the situation we were facing as a weighing equipment manufacturer. On this slide, I will show you our solutions and the benefits our customers have from it. This part of the picture illustrates the weighing equipment environment which we have to connect to the MES, ERP and to the cloud. This part of the picture illustrates MES, ERP and cloud environment. To connect these 2 environments via OPC UA, we introduced the ACI 400 edge device. The ACI 400 includes an OPC UA server with the companion specification for weighing. The solution with an additional edge device, as shown here, creates a win-win situation. For Mettler Toledo, it has the benefit that it allows to connect the entire existing product range via OPC UA to the MES, ERP, cloud environment. We have to maintain one device only. The second winner is our customer. With this edge solution, he can connect all new and all existing weighing devices from Mettler Toledo via OPC UA to the MES, ERP and to the cloud. In parallel to the OPC UA connectivity, he can still communicate with Profinet and Ethernet IP according to the SCADA automation communication pyramid. As a result, he can combine old and new architecture, meaning any-to-any and SCADA, and finally, the customer has OPC UA communication that uses the companion specification for weighing. I'm at the end of my presentation. Thank you for attending. I'm hoping I could give you some interesting information. In case you have questions, you can see my email address, eugen.schibli@mt.com. Thank you very much, and thank you to Stefan Hoppe for organizing this very, very interesting event. Thank you very much.
Thank you very much, Eugen, for that presentation. Great. The next presentation is, and this is what you mentioned in the chat here, that I'm handing over to Dr. Horst Heinol-Heikkinen. I will make you a presenter now, Horst. and we get your presentation from Asentics' point of view. We can see your screen. Just start in full screen mode. Yes, we can hear you, and you have to just switch the presentation mode. You are in the presenter mode. You have to switch in the upper line, Anzeige Einstellungen. Yes, switch, vertauschen, yeah. Perfect, we are seeing you in full screen. Horst, it's your presentation time. Thank you very much.
Okay, thank you. Thank you, Stefan. Thank you very much. Also from my side, ladies and gentlemen, welcome to the OPC Days 2021. So from my part, I will directly switch in my presentation because time is running already. So in my speech, I would like to talk about our OPC companion specification made for machine vision systems. And maybe as you know that companion specification is always a standardized information model. And this is very important because at the end, what we would like to have is a powerful tool means a digital twin, and standardized information model is a part of a digital twin. Okay, shortly, maybe I would like to introduce myself a little bit. My name is Horst Heinol-Heikkinen. I'm the COO and managing partner of the Asentics Group. And beside this, I'm also acting for two associations. One of those is the well-known VDMA, and the other one is the new founded IDTA, Industrial Digital Twin Association, founded in 2020. So in both associations, I'm quite active in the area of cyber-physical networks, and I've initiated some of those aspects they are dealing today with the VDMA and also in the IDTA. So, but on next slides, I would to give you an insight, what is machine vision and what is the Asentics Group. Okay, a group consists usually then more of one company. So we have two companies. One company is a so-called system house for machine vision solutions. That means we bring our machine vision systems directly in line to our customer. And the other company, this is the Asentics Vario. The Asentics Vario deals with also with machine vision, but it is more than an inspection machine provider. It means we are manufacturing high-speed, high-level inspection machines, doing 100% quality control on its own. So it's a machine, or let's say a huge camera, more cameras inside, but the whole machine is only to bring the product underneath the cameras. So. Okay, how does it look in real? Only two pictures. What you can see, you see on the upper line, you can see our machine vision systems, what we can bring inline to the customer, and underneath there, you can see one of our high-end machines, for example, here inspecting seals. We can inspect up to 15 seals per second from the top side, from the bottom side, from the outside, inside, could be different seals. So as you can imagine, 15 parts per second is a huge number. And the resolution of each camera is, I think it's 12 up to 12 megapixel. Okay, so stepping in means I would like to introduce you to our VDMA OPC Vision Initiative. What is it? The initiative is something we have also founded, I think, 3 or 4 years ago within the VDMA, and we would like to deal within this initiative with the OPC Foundation. And what you see here as an example, this is the standard working group, the so-called joint working group you have to have if you would like to create a companion specification. Maybe you know that, but I would like to explain the specialities with the machine vision guys within the VDMA. So I have to start here. So on the right side, you have the OPC Foundation. They are specifying and they are dealing the framework of the OPC things. And on the left side, there is the VDMA. All those member companies, they bring their special knowledge from the domain, from the machine vision industry. So, and then in the middle, you can see we design a companion specification. So this is standard, but what is the OPC Vision Initiative? We have embedded, so-called embedded, the joint working group in our initiative. And our initiative is much more than only one host. So we have 4 other hosts around the world. These are 4 more associations from the United States, from Japan, from Europe, another association, and also a Chinese association. So all those associations, they deal with our companion specification. And so they provide also information at all 3 continents. This is the reason we call it the G3, because we are talking about not 5 associations, but about G3 continents. So this is very special, and this is very helpful, because this is really a global standardization process, what we are doing there. Okay, I will lose also a few words about machine vision system, because it's maybe not so clear for everybody that we have some complexity if we talk about machine vision systems and how to standardize machine vision system, because you can see on that slide that a machine vision system is could be very different. So we have a broad system range, starting on the left side with something very simple. It's a machine vision sensor. So it's a camera with some processor inside, and it's maybe the lowest end of a machine vision system, and you can see how it scales. Maybe it could be an application with maybe more than one computer, maybe 2 or 3 and 10 or 15 cameras. And this is also what we call a machine vision system. How to standardize that? So we have to find a way when we design our companion specifications to bring a standard for all those systems, not to have 4 different standards, to have one standard. So to have a generic description of a machine vision system. Besides that, we have another problem. This is that we have enormous application variety. As you know, maybe somebody of you have had already contact with machine vision systems, and you know there are myriads of applications. So we have lots of different configurations, different results, and so on and so on. It makes life not so easy if you talk about standardization. But however, we bring out OPC companion specifications in 2 parts. So we started 2017 with the first part of our machine vision companion specification. It's called 40101. And what we did there inside is we standardized data management methods. That means we talk about how to deal with configuration, how to deal with recipe and results, and so on. So but we standardize only the management methods, not the content. The content we standardized later on in part 2. But in part 1, we also have a standard so-called state machine. That means we have a look to all those different kind of machine vision systems at the behaviors, or the behavior control and the observation is so standardized in a state machine, what you can use for a simple sensor and also for a huge machine vision system. So this is a very generic description how a machine vision system behaves. In part 2, we additionally describe a so-called asset model. That means a machine vision system is it's a computer, it's a light, and so on, and all those components are described. And also we say something about condition monitoring. So part 2 will be ready this year, 2021. I think in autumn we will also reach the end of part 2. And of course, part 3 will come also after part 2, that's for sure. So now coming, what did Asentics with all those results? What is our solution? How did we enrich our own portfolio? And as I told you already, so the market is very diverse, and so also Also, our machine vision components are, as I already mentioned, very diverse. That means we bring already in the past, and that what I show now is the old world. We bring our vision sensors, our machine vision systems, and also our automatic inspection machines. We bring them to, for communication in a standard local area network. So we have then in the old world an horizontal communication path to communicate with different machine vision systems, but with standard local area network. But then we would also like to talk to the outside world for sure. So that means, we would like to talk to a SCADA system, an IT system. We would like to talk to an MES system, or maybe we would like to watch an so-called end-on board, how the results are from all those different machines and all those vision technology, because we are producing lots of information. And it's you can nicely show them up on an end-on board. And this is a product of our own. And in the past, we connected that via a local area network. But now the new world is we talk all our products, talk OPC UA, and we use, of course, part 1 and also part 2 in the future from our company specification. But as you can imagine, maybe this is not enough. On the next slides, I will show you the possibilities to enhance with vendor-specific OPC models, also the company specification, and you stay already in the, or you still stay within a standard. You still stay in OPC UA. The platform we have designed is that what you see here. So it's a client infrastructure where we can manage on a SCADA system, on an end-on board, or even on an ERP system as an as a client infrastructure. We can deal with all the information. Doesn't matter if it comes from vision sensor or from the automatic inspection machine. So next to our implementation of the server implementation on our products, we have also client infrastructure, a so-called framework, helping our customer to deal with all those information. Yeah, and on the next slides, maybe this is also something you know already, but I would like to show that because it's very important for me to send out that even if you are not using a companion specification which is standardized by many other partners, you can also, as we did that, you can, based on the OPCR meta model, perform or design your own OPC UA extensions. You can see that here in blue color. So these are the Asentics extensions, because we have so many information also from our machinery. And a standard machinery companion specification is not yet available. VDMA is working on that, but Asentics does need that also in the past, because it doesn't help so much if we have only communication based on a companion specification for all our machine vision sensors. We do need also extended communication level for the machine, because we have so many information about the health of the machine, the state of the machine, and so on. And you will find that on this side. And please keep in mind, this is very important, you still work with a standard because you're still working with OPC UA. And if VDMA will deliver maybe in 1 or 2 years a companion specification for machinery, you easily can exchange your vendor-specific thing with the standard thing. So it's always allowed to do that. So you have a fully equipped information model, and you can talk to the outside world, even if you are not using companion specification. But it's recommended, of course, to use the companion specs. Okay, I think my 10 minutes are over. If you would like to have further information, please contact me directly, or even contact Mr. Supratek Banerjee. This is within the VDMA, our standard manager of OPC UA. and he will help you and maybe guide you through our companion specifications. You can find them also on the homepage with the VDMA. And nevertheless, if you have interest and ideas how to deal with the digital twins, then contact me also, because then maybe we can do something for you within the IDGA. So I thank you very much for your attention, and I also hope that there is something new inside my speech for you, and thank you very much for that. Thank you.
Both gentlemen, thank you very much. You really added a lot of value here to this OPC Day 2021, because I really love the way that vendors and end users, what is the next block, are sharing their experience to others and be available and not just keep knowledge for themselves. This is what I really like to thank you personally. I'm really impressed that you started extreme early. You have really realized and recognized the power of OPC UA for your companies early, and that's why your products are early on the market, and you even step forward and bringing this into a more international level. Both of you, thank you very much for your contribution to the community, but also here being guest here at the OPC Day today. So I'm now moderating. Thank you, bye-bye. We are now coming to the next block of end user reports, and I'm also giving you a short insight how I became knowledge about this story. I joined the ARC forum in February 2020, and this was it 2020 or 2019? I'm getting older, even I can't remember. But it was interesting for me, because I was walking around and talking to a lot of attendees. It's a really good networking place, as you know. And so somebody from the main sponsors, and I will not tell you the name, he contacted me and said, hey Stefan, I'm not seeing OPC UA here at this conference, and here in US it's not popular. So what are you telling me? This was on day 2 it was on day 2 of the conference, while I was sitting always super relaxed, listening to all the presentations about PADIM, about the MDIS initiative, about the OPAS initiative, and about the Namur open architecture. And all of the presentations had one common puzzle piece together. It was always the OPC UA logo somewhere on the slide. And I said, hey, that's funny. It's all around, it's everywhere. Maybe, yeah, I know MDIS, we are working with MDIS. Say, yeah, so it's based on OPC UA. Okay, that was really funny. I turned around a little bit disappointed, obviously. But okay, and then I run into a person from Equinor, and he says, hey Stefan, exciting news. We have established our oil platform, and we have connected over 180,000 data points. So my emotion immediately changed. I was happy the day was done, and that was a really good story. Equinor joined the OPC Day 2014 with a group. They learned about OPC UA. They connected to, I think, also Erich and the Microsoft people. At that time also Clemens Vastas was very active. And both gentlemen, Clemens and Erich, gave them a deep introduction later on. And today, a couple of years later, we have a fantastic success story from Equinor, and I'm really happy to have you here to share your insights. Maybe you introduce yourself and give your own background.
Thank you for having me here. It's a real pleasure to be here. Yeah, so my name is João Pinheiro. I'm a senior technical team lead at Equinor, and I'm going to talk about the strategies for data-driven digital transformation in the plant. Maybe we can start a little bit with the company. So we are Equinor. We are a broad energy company with 21,000 colleagues. We are committed to turning the natural resources into energy for people and progress for society in more than 30 countries worldwide. We are dedicated to safety, equality, and sustainability. As the largest operator in Norway, a leading international offshore operator, and a growing force in renewables, we are shaping the future of energy. Equinor's strategy is based on 3 pillars: always safe, high value, low carbon. To reach our ambition goals, we need to stay in the forefront of digitalization, implementing and creating value from digital tools. So digitalization is here to transform the way we work and enable us and support in our strategy and goals. So we need to use data to improve safety, to reduce our development and operation costs, increase recovery and discovery, and reduce the greenhouse emissions. Our digital roadmap is centered around 6 programs, cutting across the company and 3 key enablers: developing digital capabilities and leadership, utilizing the external ecosystem, and developing our unified data platform. For example, on this 3rd objective, we recently built a cloud-based data platform called Omnia. Here, relevant data is made available, irrespective of its source or its point of creation in the value chain. The idea behind this platform is to move from silos of data and across our value chain to one common platform that orchestrates all our data across the value chain. One of the areas and programs in our digital roadmap is data-driven operations. This is about using data to maximize asset value through production, optimization, and maintenance improvements. So let's start with the first one, data. Data, you simply need data to be available if you aim to run your business based on data. So the challenge in Equinor and many other industrial companies is that data is tightly coupled to the applications, where each application has their own data interface, own data model, own data access regime, etc. If you look at the second one, the context. Data without any context is quite useless. You need context to ensure that humans and machines understand what the data means in order to be able to use it. So when you have data and context, then you have information which can be used for analysis and visualization. So making data or information available to humans and machines for analytics visualization, it's critical, so we should use it. Business decisions. The final step is to make decisions faster and better based on insights derived from contextualized data and or analyzed data. So OPC UA is a connectivity framework for industrial automation data that is really supporting us and helping us to contextualize data available from our industrial automation and control systems. So here we have a drawing which shows us the heterogeneous versus the information world, so OT and IT. So we can start with the physical equipment on the bottom here. So we have the physical equipment which has a real-time embedded computer controller, and this is sending out information to a core process control, so SAS, a drilling control system, which has its own HMI. And then this data is tunneled through an OT-IT gateway, which is then sent out to process historians, which are IMSs, and this is then sent out to an historian cloud exporter, goes through a broker, and then it's stored in an Omnia data lake. And then also we have the data available on a time series database. So if we have a data consumer in Equinor that requests to have access to a certain amount of data in Omnia, they send out the ticket to the Omnia team. Omnia team prepares an API, and then it's available through this Omnia API to our suppliers, to our data consumers, or whoever wants to have access to this data. Here we have 2 examples of 2 sensors which are sending us data, but this is data without information, without context. So if you look at the 2 tags, you see that these 2 tags, these 27TT3011 and 27TT3061, they are giving us a value and the quality is good. Okay, so we have value, quality, and timestamp. However, we don't know exactly what this sensor is measuring. So it's measuring what? Is it the valve? Is it the pump? Is it the motor? Is it the outlet temperature, inlet temperature? Is it upstream, downstream? So in order to answer this, we need to have context on this data. So the most powerful game changer to obtain context is OPC UA. So it has an ability to turn data into information, data in context, with the OPC UA information model framework. Its ability is to standardize on information across vendors and products using OPC UA companion specification. And this results in interoperability. OPC UA is an open, international, industry-independent, and secure connectivity framework is supporting Equinor in making real-time contextualized data, which is information available. So this means that 2 out of the 4 pillars to become data-driven are already established. But to do this in scale and speed, we need interoperability. So it is important that we also have our vendors implementing OPC UA, so we can lift out the data from the bottom level until our Omnia in a much easier and much faster way. So our plants, they are heterogeneous, meaning that we have many different vendors delivering software and hardware on the same plant and across plants. If each vendor is delivering the same type of data in different vendor and system-specific interfaces with vendor and system-specific information models and semantics, then humans or our engineers need to spend a lot of time interpreting this and mapping and transforming this. So interoperability means that we have similar information organized and defined in a standard way, regardless of what the vendor and the system we are talking about. So we agree on common and open formats, information models, and connectivity standards, and we need to have well-defined, understood interfaces. So an OPC UA server can look like this. It can look like with a very good structure where you have the equipment, you have the system where it belongs, you have attributes, you have a nice structure. So an address space that gives you data context information powered by an object-oriented types and instances information model. So an address space where you can browse relations, you can find the connections between objects to understand how things are connected. But it also can look like this, which is really good. You have a good structure again from one of our vendors where you have the sensor. You also know that it's an analog value and you know it's actually current for phase 1, phase 2, and phase 3. And it's very easy to transform this into our model, which is basically almost the same. Now, there are also other less good examples. For this one, for instance, when we look at the analog values that this UA server is sending to us, it's very hard to retrieve any kind of context from this analog values. We know it's 1 to 27, but what are they measuring? What is the value that you're getting from this? So we don't want suppliers making their data available like this on their OPC UA servers. We, meaning the entire industry, need to agree on standard information models for given domains and assets. This is another bad example. So for instance, when we browse a server with this kind of information, it's almost impossible to know what they're describing here. So in order to be able to transform this into something readable, we have to go through technical documents and we have to map it to something that is understandable. So we know that these first tags actually represent foam, gas, oil, and sand density levels. So OPC UA has been implemented and proved in use at scale on Johan Sverdrup. So this project started production in 2019. This field alone is massive. It produced 30% of Norway's total production. And OPC UA has been a central part of the digitalization strategy since 2015. So we have in total 19 OPC UA servers on the plant floor, aggregated into a single OTIT gateway using OPC UA aggregation architecture. So let's take a look at the architecture. So if we start with the top right corner here, this corner here, we have the OPC UA library. This OPC UA library contains the template of all the objects and types and classes that are defined for all the different equipment that we have in our system. And in here, we have the engineering database. And the engineering database means that it contains all the equipment tag names from on our database. So when we merge our library, which is a template, can be used in any project, with this database, we get a plant-specific mapper, meaning that we have, on this case, Johan, we have combined all the types and all the objects with the library, and then we get automatically assigned types for all these equipments. So meaning that, for example, this well, this equipment, they automatically get assigned a type. So we don't need to do any manual intervention here. It's an automatic process. So all we have to do then is assign the class, which gives out the attributes, which we then show on the upper level. So if you go down here to the infrastructure, we have an aggregated server. So we have down here all the sensors that are sending us OPC UA data. All these sensors are then aggregated, sending out to these servers, these DIG or IACS gateway servers. The data is now available here and then is replicated to an OTIT gateway. Then when we combine the data available down here with the plant-specific structure that we get all the types and classes here, then what we get is an information model like this. And then what we do is we send out that information model to a collector. That collector stores in the data archive, and then it makes it available all the way down here for anyone with a tablet or phone or a computer. They can access to this data. So they have a visualization tool which they can access to all this data. So you see, with just this 3-step here, this one, and this one, we get all this highlighted area pre-built. There's a lot of work already done here. And then this area here is just built on this server here by assigning classes to the right equipment. Just some fun facts. Our OPC UA library, so the template, consists of 50 objects, 90 classes, and 920 attributes. So it's the same library being used in multiple assets. It's already been used in renewables as well, so it's not strictly connected to oil and gas. Our visualization consists of more than 745 pictures that are connected to this data that we have available. And our tag server has in total more than 190,000 tags, which we will upgrade soon to reach about 1 million. So there's a lot of information, a lot of models already being available on this structure. Our UA asset structure has more than 31,000 equipments. So these are the equipments that are automatically assigned the type when we do the connection between our library and the database. And they have more than 1 million items and references. So we utilize and we benefit from this community. And by open sourcing these information models, we also contribute back to the community. So you can go to this link here and you will find our library, the template library that I was showing you before. You can find it there and you can use it for your own purpose. So we believe that being open is the key to achieve adoption, and we believe in openness is the spirit of OPC UA. There are many end user benefits, but let's just highlight some. So it reduces the total cost of ownership. There's an efficient exchange of data without needing human translators in the middle. There's an increased flexibility in the overall architecture. Easy to replace, it's plug and produce components since the interface and information models are the same across vendors. OPC UA is designed for and used across industries. A supplier can use the same interface and the same information model across customers, across industries. Innovation, opportunities, data-driven operations. By utilizing the intention behind OPC UA, we get easier and cheaper access to higher quality contextualized data from our plant operations, industrial automation, and control systems. So, more access to innovation due to broader communities, ecosystems, and international competence, and more competition. So companies now need to compete on business value and not making it vendor locked in. Also, the ongoing and future areas that we need to focus on now. We need to scale up the standardization of OPC UA information models. So there's a huge potential, but we need more and more vendors to start using this so we can scale up much faster and much cheaper way. Closer integration between the plant floor and applications and the service in the cloud. This means that we need to make not only the data, but also the context available from the OPC UA servers. So at this point, our information model is kind of hidden on this silo within the OTIT gateway, but we need to expose it also to Omnia. Usage of automation ML and OPC UA together. So we need to close the loop between the engineering and operations. Alignment towards international initiatives like Namur Open Architecture, Namur Model Type Package, Open Process Automation, Industry 4.0, all of them point as OPC UA as one of the several key building blocks. And end users to have one voice towards the suppliers when it comes to OPC UA. Yes, and that ends my presentation. I hope you enjoyed it, and thank you again for this invitation, and I hope to see you soon. Bye-bye.
Thanks, and thank you very much for this fantastic success story. I love to hear this story with more than 190,000 data points being live and real. I just was answering questions in parallel, and there has been a question, hey, this success story is not based on deterministic data transfer. What about this? And so my answer, which I typed in parallel here, was, hey, remember OPC UA, when we started years ago, it was not including deterministic real-time. Instead, it's the perfect modular architecture of OPC UA, allowing to extend OPC UA with new transport capability. This makes OPC UA so powerful because there's not one single protocol which is dominating the whole industry for multiple decades. There has been multiple protocols available, but after a few years they are no longer the preferred option. And so OPC UA can exactly extend. And this is what the OPC UA FLC initiative is doing. They're extending with Ethernet APL, they're extending with TSN to add capabilities like deterministic real-time. We have the demo end of this year at the SPS show. Implementations for real products will immediately start when the specification has been released, but until we see end user stories about TSN here on the OPC Day, it will take a little bit more time. Okay, this was an excellent presentation here from Equinor in the area of the process industry. We have another proud example of a world-class company, and I'd like to ask Jan to introduce himself from BASF.
Hi, this is Jan from BASF, and together with my colleague Timo Himmelsbach, I prepared this talk on production data integration at BASF. Before we dive into the topic of production data integration, a quick overview on BASF. So we are one of the largest chemical companies in the world, and as you can imagine, we have production facilities scattered all over the planet. Some of our sites are smaller, where we only have 1 or 2 plants, but we also have several very large integrated chemical parks, which we call Verbund sites. We have them in North America, in Europe, with Ludwigshafen in Germany being our headquarters, and we have them in Asia. This concept of the Verbund is something that you will find across the entire company, and it actually means a very deep integration. When we talk about the Verbund in terms of production, it means that we have the whole value chain on one physical location, and we have the products being made in plant A becoming the raw material for the next plant, and so on. And in the same way, we do a very deep integration of our utilities within these Verbund sites. And this we do similarly with our entire value chains, with our markets and customers, and even with technologies that we share across a whole wide range of segments. And of course, in order to really capture the benefits and synergies of such a Verbund, you need digitalization to be able to harvest these advantages. So the key question now becomes how to enable digitalization. And given the name of this talk or of this session, it's not a big surprise that the answer is through data. And then the question is, okay, so how do we integrate this production data? Well, in the recent past, that looked more or less like this. We had our plants, which had a control system and also a functional safety system. And some 15 or 20 years ago, we realized that it would make sense to capture the data of these control systems in databases or historians, and that's when we introduced the production information management systems, which was then used by people making some simple calculations and dashboards. And as we were using more and more of this data wasn't only relevant for people working, let's say, in an OT environment, but this was also data that became important for people working more in the corporate network environment. And so we naturally started having this automation pyramid where we had strong segregation firewalls between the different layers and this need to share data across these layers. And of course, above the corporate network, you have another firewall which separates us from the public internet. So this is how we did it in the past. The problem becomes really interesting when you talk about global data integration, because then you're not talking about one automation pyramid where you have one control system with data and one PIMS that you want to integrate. Now, then you're talking about a global landscape of different kinds of plants with different ages, with different kinds of control systems and different PIMs. And then you basically want to solve this problem of integrating data vertically in your automation pyramid on a global scale and integrate that data globally. And this is a whole other challenge. Because in this case, when we look at the data providers coming from this operational technology, we suddenly have all kinds of control systems, different kinds of PLCs, SCADA systems, DCSs, batch systems. Depending on the complexity of the plant, that might look completely different. We have different vendors and we have different decades when these plants were built and these control systems implemented. Similarly, for the PIMS, we have all kinds of vendors. We have PIMS for the continuous plants, but we also have PIMS batch modules for the batch plants. We even might have some plants where we have additional data stored in SQL or Oracle databases, etc. And we not only want to integrate the process data, we also want to integrate this batch data to have contextualization. We want to integrate the alarm data, and we even want to integrate the field device data to have a really good understanding of what's going on in the plant. So the problem becomes even bigger. But once you're able to do this, then of course you have this wealth of data that you can make available for all kinds of applications. And in this case, you can have more traditional things like an alarm management system or control performance monitoring. But at BASF, we also have a reliability center, which is an expertise center localized in Germany that looks at large rotating equipment on a global scale. This data can then obviously also be used for predictive maintenance applications. We can dashboard our manufacturing execution systems, and we can do vertical integration with our ERP system to make a close tie-in to the supply chain. And when you're talking about this kind of integration, in the end, you're talking about managing complexity, because we have not only the complexity of this vertical integration across the automation pyramid, but we have this complexity with this heterogeneous legacy technology. When we look at the pure hardware level, we have old machines, old servers, old PCs running Windows XP, running all kinds of Windows Server operating systems. We have different software, different vendor solutions and versions, which means that if you integrate a certain version of a piece of software on some machines, it works well, but on other machines, the performance is not working well and you're crashing the machine, even though you're doing exactly the same as what's working in your other plant. In terms of protocols, we have a wide variety of things to integrate. So we're looking at OPC DA, OPC HDA, OPC A&E, which at least are standards, but we also have a lot of vendor proprietary things. And what we've learned at BASF is that when you really want to do global data integration and streaming of large amount of data, so a typical chemical plant might easily have 10,000 tags or more, and if you want to integrate them on a 5-second frequency, then you run into performance problems. And we've seen that these more standard protocols or the interfaces offered by the software vendors might often not be good enough to really allow this kind of streaming. And then you need to look at vendor proprietary solutions because they are better integrated within the software of the PIMS vendors, for example. But then you need to write your own interface to get that data out of the system. Security is, of course, another topic. So 15, 20 years ago, we were happy when we could solve the technical problem and security was maybe not such a strong dominating force yet. But nowadays, of course, we need to make sure that when we integrate this on a global scale, we have the security also under control. And a lot of these older solutions are not really good with that. On the other hand, we will not just migrate everything away because of the old saying, never touch a running system. So we need to live with the fact that we know that there are security issues and need to come up with workaround solutions to make it as secure as possible. And all this heterogeneity is then not only on one location, but we have this geographical distribution. And then network performance and bandwidth becomes an issue, of course, and this global network integration, routing and firewalling. So in the end, you have the challenge of integrating a certain piece of software on an old machine running somewhere in South America, and that needs to transmit data to a corporate center somewhere in Germany, or exchange data with some colleagues in Malaysia because they have a similar plant. And this kind of geographical distribution adds another layer of complexity to the whole puzzle. Looking at the current status at BASF, I would say that we have managed this complexity and we've been able to integrate hundreds of plants on a global level, and we're using this data for all kinds of applications. But the question is, of course, what's next? And we have seen a lot of innovation in the last years with mobile devices, Internet of Things, and the introduction of the cloud, where we have new possibilities with big data, machine learning, artificial intelligence, which enables us to explore new service and business models, get better intelligence and insights into our plants. And the question is, of course, how we can leverage these kinds of benefits. And so we as BASF, we are looking at how we can leverage this kind of innovation while keeping everything that's good within the automation pyramid, because we have systems here that will still run for the next 10 years, but combining that with all the new chances coming through cloud and IoT. And what we're proposing is the Namur Open Architecture, which is an initiative strongly driven by Namur, the user association of automation technology and process industries. And we see NOAA as the fast lane for all non-core process control relevant data. And how could this work in practice? Well, the IoT sensor that we would use to retrofit the plant, while it's physically inside the plant, it has actually logically nothing to do with the control network, because we don't use that to control the plant. We only use that for additional monitoring and optimization. So it actually makes complete sense from a network point of view to separate that from the control network and to use that directly within the fast lane and make sure that you can integrate that data as soon and as easily as possible. Similarly, for the existing field devices or shop floor equipment, there is a lot of internal data, health status, additional measurements, maintenance information, things that are there but that we're not using enough because in the past we never integrated that in the DCS. And since our DCS systems are old, doing all of that retroactively is very, very hard. So here we're proposing to use a second channel for monitoring optimization and to get that data out of the automation pyramid and integrate that as well through our fast lane. But of course, since this is a device that's already connected to the automation system, here we need to take care of security, and here we have defined the NOAA Security Gateway as the solution to get access to this data without influencing the control system. And one way how this could work in practice is you have a hard field device, which in the past was only connected via 4 to 20 milliamps to the DCS, and now you're actually using the hard protocol to get access to that data, but instead of integrating that in the DCS and then from the DCS to the PIMS and from the PIMS to your global data integration, you integrate that data directly from your NOAA gateway into your NOAA fast lane. This concept has been described in the NAMO recommendation NE 175 and is the way how we as BASF see the path forward for these new innovations. This will then basically allow us to leverage this innovation, but of course we also face new challenges. Because we will have a huge increase in data sources, this will be an additional complexity to manage. At the moment we have in one plant, one PIM system, but now we're retrofitting this plant with additional industrial IoT sensors and solutions. So we will have new connectivity, maybe using mobile with 4G or 5G, using low power wide area networks like LoRa. And these new solutions, they don't come with the old automation and OT protocols. No, they come with IT stuff on board. So they speak MQTT, AMQP, and Kafka. So we suddenly have a stronger introduction of IT within the whole OT landscape, which is something that we need to be able to integrate as well. And then, as I mentioned, this additional monitoring data from the existing field equipment will mean that suddenly there will be a lot more additional data sources within our plant. And so the only way for us as BASF to have a realistic chance of integrating all that data is by reducing the complexity. How do we do that? Well, as BASF and as NAMUR, we are really driving standardization. And standardization from our point of view is not something you can do in one discipline, but that you need to do across several disciplines in order to get a full solution. So in terms of the physics, we're really pushing Ethernet all across the automation pyramid. And we see with things like the advanced physical layer that we will get Ethernet all the way into the field, even into our hazardous areas. But Ethernet is not enough. We also need to standardize the language. And here, something that has really evolved over the last few years is that the industry has more and more embraced OPC UA as one of the dominating protocols on the shop floor. And therefore, this is also a very important topic for us as NAMUR and BASF to push forward. But again, physics and language is not enough because you also need to standardize what's being spoken. And here we push the standardization of information models, and something which we have been able to achieve through the NAMUR Open Architecture initiative is really drive this standardization from a use case point of view. So we defined use cases that we wanted to achieve for our field devices, then defined what kind of parameters we needed for that. And this has now been modeled in the PADIM companion spec. So PADIM stands for Process Automation Device Integration Model. And what this means for us is that any device in the near future that comes equipped with PADIM will be a device that delivers exactly the parameters we need for our use cases in exactly the format that we want. And again, this is a huge step forward. But unfortunately, it's not enough to have this standardization. What we're also pushing at BASF is to leverage cloud-native technology. And I mentioned when I talked about managing complexity that this whole hardware dependency and also these chances that we have through the cloud, that this brings additional complexity. And here we're looking at a way to abstract away actually this kind of hardware and middleware heterogeneity. And this can be achieved through architectures based on microservices. So you would have a piece of software containerized, which could run on any location in a hybrid infrastructure. And this is how we see the future of our IT landscape, is to have public clouds combined with private clouds, combined with edge computing. and where you would have one piece of containerized software that you can pretty much deploy anywhere. And this would give us an independence of hardware and middleware. And in the end, what we want to achieve with that is that we would be able to regionally integrate our data across our automation pyramid or through NOAA into a cloud platform, and then do the global integration on this cloud platform, but through microservices that we can deploy wherever and whenever we want. And that for us would be the final solution for global data integration. And with that, I would like to say thank you very much for your attention.
Thank you so much, Jan. Impressive presentation. I'd like to thank you again because you supported us already at the ARC forum begin this year. And now again, thank you so much. This was a blog about the process industry. We are now moving over to the automotive industry. We had one of the questions yesterday, hey, Microsoft has been very prominent. Erich Bahnstedt did a fantastic presentations, and there have been a couple of success stories already. What is about the other hyperscalers? And here exactly is one of the success stories between company Renault and Google Cloud. So let's listen.
Hello, I am Thierry Daneau from the Renault Group, and I would like to share with you the subject how to structure and capture industrial data with scalability. A short presentation of my personal background. I have 35 years of experience within the Renault Group in various professions such as maintenance, process engineering, industrial IT, and automation. I work in France in the Renault Techno Center located in Guyancourt near Versailles. Since 1916, I have been working as an expert on automation and robotic technology and architecture. As such, I enlighten the company on the technological choice for the future of our factory. I am also product owner for the industrial data capture project for Renault Group. A quick overview of the Renault Group in the few figures. Renault, it is 5 brands, Renault, Dacia, RSM for Renault Samsung Motor, Alpine and Lada. And one alliance with Nissan and Mitsubishi. For the Renault Group on the industrial side, there are 38 production sites and 13 logistics sites in 16 countries. Regarding production volume, we produce more than 3.5 million vehicles and about as many engine, gearbox and chassis. In 2016, Renault launched numerous digital initiatives in a benchmark factory in Spain. From this experience, in 2017, we launched many digital transformation projects. This project revolved around 5 major pillars: real-time data-driven operation, full track and trace, flexible supply chain and plant, process 4.0, and connected workforce. The subject that I will detail in my presentation lays the foundation for several transversal subjects. Regarding the subject of industrial data, over time we have accumulated numerous technical solutions which have partitioned the data by typology. For several examples allow me to illustrate my remark. An example on traceability in powertrain plant, an Atlas Copco system when we have Atlas tightening controller, and for conditional benzene maintenance and robot, we have a specific system per brand. If we talk about automated installation, we have installation from the 18th to today and significant diversity of automation and protocol components. Each of the technical solutions has its own architecture, and when we try to mesh data, it is very complicated. When we look at industrial installation, we have a lot of data from industrial equipment such as PLC, input output, Boolean, robot, vision system, variable speed drive. If we look at the functional need, we need answer on product traceability, process traceability, measure, state of stock, photo, and video. For end customer, we see that data is of interest to many businesses in the company: quality, energy consumption, maintenance, automation, and manufacturing. To meet these multiple needs, we have defined a standard for data capture, and we have a strong slogan that is spread for the company with a common target: collect once and use many. For the capture of industrial data, there are two essential layers: the industrial layer, repository layer, where we have defined the data model and the single publication table; the data acquisition layer, where we collect structured data from different industrial equipment. The condition for success for this digital transformation to succeed: the common data dictionary, the unified information structure, the granularity of the data for a maximum of use case, a worldwide standard, a common automation and IT approach. To meet this condition, we have chosen the OPC UA technology with the approach of data model. This element will make it possible to meet the challenge of the factory of the future, where we have unified data capture, interoperability, machine-to-machine communication, edge, cloud, and big data, machine learning, artificial intelligence, and digital twin. Here is a quick overview of the architecture implemented with 3 levels. A first level at machine level, where we have implemented a software we call UDC for Unified Data Collector. This software transforms all proprietary protocol into OPC UA with a structured data model. A second level at the factory level, where we have implemented a software we call DFA for Data Flow Aggregator, where we aggregate factory data to send them to the internal cloud until mid of 2020 and Google Cloud Platform since that date. Some interesting data on the capture of industrial data: 3,300 devices deployed in OPC UA, 300 billion data collected since the start of the project, data from 17 factories representing a flow of 10,000 messages per second. We use OPC UA technology for Industry 4.0. From Industry 4.0, we have more than 1 million measuring points. We collect different forms of data: Boolean, string, analog value, table, file, and image. The organization we have to implement all the fundamentals of the data capture project are a team dedicated to the data model, made up of multidisciplinary group from OT, ISIT, and process engineering, which has already made 40 data models for the powertrain plant, 10 data models for the vehicle plant, with a target on the creation of 200 data models. A team dedicated to software development with 4 fundamental building bricks: Magic Door plus add-on for data model, UDC for industrial equipment, DFA for aggregation, and Google Cloud Platform for the publication table. The target rate is to be plug and work. A deployment teams made up of factory and corporate automation engineers to implement in the UDC in industrial facility. We first deployed 100 piece equipment in 2018, 900 in 2019, and 2,000 in 2020. The current target is to deploy on a large scale. An OT and ISIT monitoring team to monitor the performance of the complete flow. We have added additional information in the data feed to qualify the end-to-end performance, and we have a real-time dashboard to see all the events. The target is to have an incident rate below 0.5%. I propose a small demonstration that we install on Renault. A rapid overview what we have in our plant. You see on the screen the central DFA supervision, where we have the complete view of what data we collect in different plants. The first information you see here is the number of value collected per second, and we have more than 10,000 value per second collected. We have here a second value about the number of subscription. We have here more than 1 million of point of measure collected, and we have here more than 700 OPC UA server implemented in all plant. And here you have, for each plant, the view of the collected data and the volume of collected data per second. And if we click in, we don't have time, but if we click, we can have the view of each plant, how many server, OPC UA server and equipment connected in each plant. The second screen I would like to show you is the number of equipment connected in all plants where we collect data. We can see we have made a ranking of connected factory, and each color corresponds at each data model, specific data model. And we can see here in the most connected plant we have robot, motion device system, we have tightening controller, we have PLC, and we have another manual tightening motion device, function controller for welding point, an energy controller where we collect information about consumption of power, of electricity in each installation. With all this information, we implement in different factory many data model we have decided. And the last dashboard is the number of data we collected in all plants, and you will see we have 17 plants where we collect data. We have approximately 700 OPC UA server, and here we have approximately more than 3,000 equipment connected in this. And we have typology of data, file transfer and value, and the volume increased since 2 years with a very huge volume collected. At the end of 2019, we launched a program called Industry Data Management 4.0 to have a unique approach for the company on industrial data. At the data industry referential level, we contextualize the data to create digital avatar of vehicle process operation. At the data operation level, we develop all the use cases requested by factory. The ambition is to break down silo for manufacturing and the supply chain and improve performance. Google, with Google Cloud Platform, bring us their know-how on big data. Because we have contextualized the data, it's easy to develop use case with the unified data. An example on robotic area in body shop and from the data we have developed 3 use cases. The first concerns the monitoring of robot and roller table cycle time to identify workshop bottleneck. It is based on the data from the PLC. This use case is deployed in 10 factories and has generated significant saving in 6 factories. The second concerns the detection of sticky point on welding gun and rely on the collection of torques and position information from robot and vehicle information from the PLC. The third concerns the monitoring of parameters where the welding controller we seek to identify the drift of physical quantity to anticipate breakdown on welding gun. This made it possible to reduce the maintenance workforce. This is no longer any need to manually measure the resistance of the welding gun every week. To end this presentation, we would like to present our vision of the world of industrial data. Our dream is to implement OPC UA from machine to cloud. As the data is structured in the machine, it can be used by all IT systems from the dashboard, MES, ERP, or the cloud. This will ensure two-way communication, bidirectional communication, without modification and without development. We imagine an ideal world where the data will circulate without modification, only with configuration. For the long term, we believe that car manufacturers should work together to share a unified data model to avoid work at our machine supplier. From structured information, it is conceivable to have a rapid deployment of artificial intelligence and machine learning, and Google will help us to achieve it. In conclusion, we believe interoperability is a key part of the factory of the future. Group Renault have chosen OPC UA technology to achieve this. Thank you very much for your attention.
Thank you so much. Fantastic presentation. And as you have seen, not only Microsoft, as before with the Equinor success story, now it has been Google Cloud with Renault. A fantastic success story from France, and now we are moving to South Germany, to BMW, and we hear another success story. I think this time it's again Microsoft. So let's listen to Dr. Backhaus.
Hello, ladies and gentlemen. This is Dr. Backhaus from BMW. Thanks for joining today's talk about OPC UA at the BMW Group. And I would like to focus on edge computing and OPC UA as a success factor for future manufacturing. Yeah, so as you can imagine, I would really love to talk about cars, but today's talk unfortunately is not about cars. It's about leveraging edge computing and OPC UA for our future production systems. And with having that in mind, first look back in the current situation. As you can see, the mess on the left side, a symbolical picture of our IT production landscape. We have a lot of different hardware for each of the production steps. A lot of suppliers have proprietary standards. The shop floor and its IT systems, of course, have different stakeholders, for example, for maintenance or quality inspections. And a lot of plants, they create their own solution, and these are not known to the central IT. So our main goals for the future are standardizing the custom solutions and the interfaces to get a better maintainability, and that focuses not only in the IT but also to the shop floor, in that case then using OPC UA. Of course, also data-driven is becoming more important, so the easy data access, for example, for analytics use case is really helpful. But of course also the global scaling possibilities are big topics, because the overall goal to create a breathable production system which is possible to scale throughput plus minus 20% at any point is a big topic we are currently working on. And as I said, I want to talk about edge computing and OPC UA. How do these two connect? So at BMW we have a cloud-first strategy, but of course there are use cases for edge or needs that we need some edge computing. First of all, control loops or latency requirements. Second, of course, where we have some spherical devices that we have to directly connect, for example, a camera. And of course, in a lot of use cases, we have a high data volume where we then want to do some pre-processing to reduce the throughput to the cloud. And of course, data privacy, some kind of data should stay inside the plant or the enterprise barriers. And that works quite well together with OPC UA. Because with its standardization, it's a big benefit to the goals we've seen on the first slide. Also, of course, with the information models and companion specifications, for example, for robots, that helps us a lot. Third topic, of course, the interoperability of the components with using OPC UA, and especially using cloud, public cloud, and edge computing. Security is a bigger topic than before. So with the functionalities OPC UA offers, that's a big help for us leveraging these technologies. So looking at our IT target architecture for 2030, and as you can see by the name, that's something we're currently working on. We're not completely there. You can see in the middle that biggest part of our IT landscape will sit in a public cloud. And on the left-hand side, where you see shop floor logistics IT, in that case, that's on Microsoft Azure. In other cases, for example, for our Cloud Data Hub, that is sitting on AWS. I want to highlight some major things here in the picture. First of all, the integration layer in the middle part, where we're doing some decoupling of services on the IT, but as well as on the shop floor side. Main technologies there is based on Kafka for streaming service and API gateway for more the REST-based interface side. And two big topics I want to talk today is, for example, the edge platform and edge computing, here highlighted in yellow, and OPC UA is our common standard for equipment connectivity. Of course, we will have some legacy world because we really have long-running equipment, over 20 years or so on the plants. But OPC UA is definitely the way to go here for the new architecture. Yeah, so focusing first of all on the edge platform and its capabilities. So a little abstract picture of the one we've seen before, focusing on the edge device and streaming service. Edge platform consists of three main parts, which is the provisioning service, device and application management, and the edge store. And all these three enable the business departments and also IT departments to centrally manage and operate and configure apps like OPC connectivity app to deploy them to the shop floor to an edge device. What are the main features in a life cycle of such application? And these applications are also used in a self-service manner by our business departments, like, for example, maintenance. They can find, install, and manage their application. They can also operate and roll out them using all these functionalities, and also if they are building up some new application, they also can contribute them to the rest of BMW, share them across plants, across countries, and make them globally available. Main benefits are for us in that case also, we focus here on standardization. So all these applications are packed in Docker containers with central IT policies. As I already told, the contribution from different departments is possible. We're focusing on hybrid approach, so that edge device could be an industrial PC directly sitting at a production line, but it also could be an on-prem data center, so on a higher level. And also with that platform, we are enforcing security functionalities like container checks or device policies. But of course, the most important use case on the edge is machine connectivity. So not only southbound connectors, for where OPC UA is our main focus, but of course also data transformations, and then to provide them on northbound to other cloud services or the streaming services in our case. And we're focusing on OPC UA. I would also like to introduce the main phases of what we've done in the past during right now. First of all, of course, in the first step, you have to establish OPC UA as a standard for new equipment. So first of all, then of course that started with some tests and so on in our production sites. And so all new equipment is at least OPC UA ready, has OPC UA service on board, and can be integrated in the future into new applications. Then during operation and building of cars, OPC UA works good together with our edge functionalities. With OPC UA as a standard, the central managed rollout and changes in the data access is easy possible. Also from business departments, for example, for failure analysis, the flexible and ad hoc data access is really a key success factor. But of course also for the integration of new IT application, that's a big help with the common interfaces companion specification, which OPC UA is providing. But of course also if you have to do some replacement or some modification in your production equipment, you can do that across suppliers if they're all sitting on the same companion specification and OPC UA standards, which makes it also really easy to integrate and exchange here. I would like to focus in the next 2 slides to use cases. Of course, there are a lot of other use cases which are rolled out inside BMW. I would like to highlight 2 of them. First of all, the dust analysis on the edge in the paint shop that you can see here in the background. In that case, we have the edge device you can see here, which have some connectivity to sensors, but also OPC UA connectivity to PLCs to get some more information about the whole environment, where we are doing then a particle analysis model directly on the edge and just providing the results to a higher IT production systems to ensure quality here in our paint shops. The second one is not the classic data use case, so to say. It's in the field of autonomous transport system, and you can see one of these robots. They are traveling around the plant, and of course there are some cases where there are doors, and in that case we are also using edge devices with an OPC UA connector to the PLCs to control these doors, so open closing doors. And also in that case, our ATS fleet service management also sits in the public cloud. So that's really already in the target architecture an application, and that's also already used in our plants. Yeah, we're not only doing that for our own, we're also doing that in a community. That's why we founded, together with the colleagues from Microsoft, the Open Manufacturing Platform. After that, also a lot of other companies joined us, as you can see here on the logos. Currently, we're working in different working groups, for example, reference architecture, semantic data structuring, or autonomous transport system core services, but also on IoT connectivity. And IoT connectivity focus on, of course, some architecture discussion, the sharing of know-how and best practices, but the main focus is it's about developing code together and provide them as open source. And all that is based also on OPC UA as a common standard there. And if you would like to join, just go to openmanufacturing.org and click there to join us or get some more insights. For example, you can also get our white papers there, and we will happy to get new members there. Yeah, that was my presentation for today. Thank you all for joining. If you have some questions, please get in touch, and have a good day. Bye bye.
Beautiful car. Thank you so much, Dr. Backhaus, for the impressive presentation. We already had yesterday some questions about the Open Manufacturing Group, so you have now all the information and the link, and please contact them directly. This was automotive industry. Now we are switching to a company, Miele, which I earlier announced is just located about 10 kilometers away where I am located here. And so it's a personal pleasure for me to hand over in a second to Christian Stickling from Miele. Obviously, Miele here in this region is well known, not because it's a huge company and a lot of people are working there, but well, the results, wash machines and the dryer and so on is obviously nearly everywhere here, also in my house, because they work forever, right? That's exactly the promise, and this is working. So I'm handing over to Christian.
Hello, my name is Christian Stickling and I'm working for Miele as an IT architect in Gütersloh, Germany. Today I would like to introduce you to a project that we implemented in the summer of 2020. First of all, a short summary about Miele and a short summary of the efficient cooperation with the OPC Foundation. Miele is a world-leading supplier of premium domestic appliances for cooking, baking, steam cooking, refrigeration, freezing, coffee preparation, dishwashing, laundry and floor care. In addition, there are dishwashers, washing machines and dryers for commercial use, as well as a washer, disinfector and sterilizer for medical facilities and laboratories. The latest product in our so-called business area, professional, is an air purifier. Founded in 1899, the company operates 8 production sites in Germany, 1 plant each in Austria, the Czech Republic, China, Romania and Poland, as well as the 2 plants of the Italian medical technology subsidiaries Stilco Group. Sales in the fiscal year 2020 were around 4.5 billion euros. Miele is represented in nearly 50 countries by its own sales companies or through importers. Worldwide, the fourth generation family-run groups employs around 21,000 people, about 11,000 of them in Germany. The company is headquartered in Gütersloh, Westphalia. Now I will show you important milestones of our cooperation with OPC UA that started in 2017. Right from the start of our cooperation, we set up an internal working group including all our plants. In the focus were our machines that produce our products. The working group decided that we will use the OPC standard in our facilities consequently in the future, certainly where it makes sense. Now, a few years later, we have worked out blueprints that we are going to extend permanently. In these processes, generated data are grouped and qualified ongoing. Thus, we build the base for communication, for example, to connect safety and secure, maybe up to the cloud. In 2017, Miele became a member of the OPC Foundation. My special thanks to Stefan Hoppe for his helpful support. A decision we have not regretted until today. In 2018, we have had a partner pod on the Microsoft booth at the Hannover Messe. To illustrate, we have shown a simple connection from the PLC to the Azure cloud. Thanks to Erich Barnstedt and his team. This opened up for us a network to other companies with the same requirements. This slide shows Dr. Stefan Breit, Executive Director for Technology at Miele, who visited us at the booth. It was a very great experience. In the past, the office application and the industrial world were strictly separated. Today, we bring the best of both worlds together. That was the overriding task in summer 2020 during our company holidays, when production was shut down, expect maintenance work. The challenge was to remove the existing hard and software of our press center, to install new devices and test them under real conditions, using of course a new communication layer based on OPC UA. Additionally, not all PLCs were ready for OPC UA. That means PLCs must be converted. A failsafe bypass had to be installed too. That all in a short time span of 3 weeks. This was a hard bit of work, particularly considering the fact that production had to continue safe on after that. Why did we do that? The aim was to establish a solid and simple solution to connect a higher level layer. For example, MES, databases, plant simulator, or to the cloud. Connecting device made up, thanks to OPC UA, an effort of about 5%. All higher levels took more attention. Estimated for data mining about 10% and build helpful dashboards about 50%. Advanced data analytics was the biggest part. To combine process knowledge with data science is very difficult, not only for technical reasons. We are not talking about rocket science here. But there are many pitfalls when you want to adapt modern communication technology to historical grown production facilities. Step by step, we are scaling even more in OPC UA. Background for this is to minimize tasks for the suppliers. Right now, we are evaluating a method and information platform. A central unit where all clients can get answers to their questions. A typical question is, here is my quantity, who is my OEE. And here it is. More questions can be answered with more extended method on the platform. A central useful storage of methods. Last but not least, we need security. It is indispensable when we talk about global networking. For example, connection plans to the cloud for service reasons. With OPC UA, we get an encrypted, solid communication. We are well positioned for the future requirements. Miele, OPC UA and the OPC Foundation is a success story, and it will be continued. True to our Miele claim, immer besser. Thanks for listening.
Thank you so much, Christian, for this really fantastic presentation. A lot of value insight, and this is what I truly believe also to speak in the name of the attendees listening here. I just realized that a few years ago I was a little bit thinner and I was more official with a tie, but time is changing, okay. Impressive here, you again connected to Microsoft Azure. I also realized that SAP is involved in your company, so you see, we all see that again, having multiple data sources, but moving them condensed into make them available for the IT helps a lot here. We are at the end of day 3 of the presentations. Before we go into the Q&A, I really like to say thank you to, first of all, again, all the speakers here. I think this was an amazing experience, which we never did before. We never really gave device vendors and end users a chance to share their knowledge. So this was a good experience. I think we should do much more of that. This is high value. I also like to thank all attendees here for sharing the time. Hopefully you enjoyed it, but stay online for the next Q&A minutes here. But again, first of all, thank you for joining.